Sad didn't. Sad. Do not wait for it.
Okay, so yeah, I'll start, and Shahaf hopefully will join us soon. So yeah, hello, thank you guys for having us. I'm Itamar, and I'll be presenting this work I did with Shahaf. It's actually I'm a soon-to-be PhD student, and this is actually my master's thesis work. And we recently presented in ICLR, so 1 or 2 months ago. And yes, so hopefully Shahaf will be here and then present himself too. But maybe we can just start. So I just sorry for this, just want to check is it an option to join now or, okay, I'll just start. So, okay, so just some brief agenda, what we will be showing today. So we'll be first showing the circuit discovery problem, which our work is concentrated in, and some motivation for a formal perspective. Here's Shahaf. I think he joined. Okay. And we're giving some short preliminary about neural network verification. And then we'll be starting to show our work of first introducing some robustness notions we defined and some empirical results where we achieved those, and then some theoretical results concerning circuit minimality. So yeah, let's just start. I think it will be more clear. And yeah, feel free to ask about everything, and Shahaf and I will be happy to discuss things here. So just like a short note about circuit discovery. So circuit discovery is an open problem in mechanistic interpretability, a central one, that concerns finding a circuit where a circuit is a subgraph of a neural network that is responsible for some computation or behavior within the full network. And of course, like the examined granularity of this circuit varies. I mean, we can look at circuit of neurons or of circuit of layers or attention heads, and that's something that can have a different granularity. And we know that some works that discovered circuits in vision, like the one presented by Crisola, and other works that concerns circuits in language models, like the one of the IOI circuit. And just to be more precise, we'll be giving some short methodology of and definitions of circuits, mainly notation, so we can have easier time talking about this. So let's start with having some neural network whose computational graph is G, which again, the granularity can vary. We can look at a graph, a computational graph of neurons or of layers or attention heads or of filters of convolutional network. But once we have like this computational graph, a circuit is induced by patching, which means like setting the complementary of that circuit, of that subgraph, to some values. So here we have this notation of C complementary, which is the non-circuit components. And we have also, I'll be quick with this notation, we denote as fg of x the inference of the full model G on x, and fc on x with the complementary as alpha to inference through the circuit with the patch, with the complementary of that circuit patch with some alpha. So let's say when we talk about zero patching, we have some subgraph C, and we set everything that's not in that subgraph, the complementary, to 0, and this is what this can be noted that way. So just basically that's what we're talking about. We have the full model G, and we have this circuit of the bold black lines here, and the non-circuit components are patched with the alpha here in gray. And how can we check if a circuit is faithful, meaning it's indeed responsible for some behavior within the full network? Well, for that, we use some faithfulness predicate, which is just like a predicate that's taking the logits of the circuit, the circuit with the complementary patch to some value, and the logits of the full models, and check their alignment under some metric. For instance, we can look at the logic difference, which is common in this type of works, checking that some logits are bounded by some delta between the full network and the circuit. And we can look at abs max and other types of metrics we consider. And so the methodology is basically to have a full model, to run a forward pass, getting some logits, and then to have our circuit with the complementary patch to some value alpha, which can be 0 or mean patching or other choices, and check that the logits of the circuit and the logits of the full model are aligned according to some metric. And if that's the case, then we can say this is a faithful circuit that is indeed responsible to implementing the computation within the full network. And obviously, circuit analysis is a central problem, also has been proposed for AI safety. And the recent work also studied this from a complexity theoretic lens, formalizing many aspects. But despite this, the existing discovery methods rely largely on heuristics or approximations. And for instance, small perturbations in the inputs can achieve different results of circuit faithfulness. And also common patching choices, putting like in the complementary, what we denoted as alpha, are also kind of heuristics. And we wish to give some formal perspective to this process. And before starting by showing this formal perspective, which concerns some robustness notions we present and other elements, we first show a short note about neural network verification, which we used in this work. By the way, Shahaf, are you here? Can you hear us? Okay. I think he's still not, so hopefully you'll be joining and be able to. Okay, so we'll be now just giving a note about the neural network verification. So neural network verification problem is that of having some network, which we, again, with our notations FG, and that takes some input X and outputs Y, and we want to have some input specification over X. For instance, have X, if that X is an image, we would like to have this image to be bounded, let's say, by some epsilon, so we can have some noise up to an epsilon in every pixel. And we want to have and we have another specification over the output. For instance, that the prediction of that network will still be cat, or for instance. And the neural network verification problem is about formally verifying that for all inputs that satisfy the input specification, that, for instance, all values that of pixels within some range are for all input specification, for all inputs that satisfy the specification. We would like that the output specification to also hold or not hold. If, for instance, if that's the output is, you usually encode here some unsafe output specification. For instance, predicting that this cat image is a dog, and then we can formally verify if under some perturbation domain over the input, the network is always correctly predicting cat or not. And there are neural networks verify that although this is an NP-hard problem, there are some neural networks verifiers that can solve this problem and basically allow us to verify whether all inputs satisfy some property on the outputs. Okay, so now we just start by showing the robustness notions with the formal notions we present here. So we start by showing the first robustness notions, the robustness notion, which is the input robustness, which this is actually really robustness over the input domain, which basically means that we would like our circuit not to be just correct on a finite set of samples, in this case, correctly predicting that this sample of cat is indeed a cat, but we would like it to be robust over this input domain, meaning we would like it to predict that also over a continuous perturbation domain around this cat sample, it will be still correctly predicting cat. So we basically demand that our circuit will remain faithful, which in this case means correctly predicting cat, not only over a finite set of inputs, but over a continuous input domain. Which makes sense because obviously a good circuit should match the full model and predict cat, not over some specific sample of cat, but also over noised samples in the perturbation domains around it. Yeah. Any questions by now so far? Sorry. Okay.
Yeah, one question. Does this neighborhood depend on the input or no?
No, we can. It depends on the epsilon here, which we can look at the bigger perturbations domain or smaller. If we take too big, then it will be very blurry. Let's say, can get also very blurry samples. But yeah, it depends on.
Please further defining how you are doing the perturbation in the inputs themselves.
Sorry again, didn't hear.
So how exactly are you formally defining the kind of perturbations you're doing to the input?
So yeah, we'll be showing that this is something we can achieve by neural network verification. We can have this input specification saying that we look on this perturbation domain and verify that indeed the circuit matches the full model and correctly predicts cat for all inputs in this perturbation domain. But for now, we just define this notion that we would like that not only some finite set of samples will be the circuit will be faithful on, but over a continuous input domain around it will also be faithful on.
I'll also update that I was able to join a few minutes ago, so sorry about being late. And to also address the question, basically it could be also defined on any possible continuous domain, like the verifier could be used for any continuous domain, but in this paper we just take like a set of inputs and then look at the surrounding around these specific inputs. Yeah, if that makes sense.
Okay, great. So once we have this robustness notion, the question is, how can we in practice say if one circuit is indeed input robust? How can we certify circuits that are input robust? Well, for that, we use the neural network verification that we previously discussed. And how can we achieve that with neural network verification? Well, we introduce some CMEs encoding that basically duplicates the full model and the circuit. And what we do here is we take an input neighborhood around the input. So in that image of cat we previously saw, we can take an input neighborhood around that image of cat. And we have the logits of the full model and the circuit. And we put here some criterion on the output, which means that the model and the circuit are aligned. For instance, we can look that they are both the winner logit of of the cat class in both models is bounded by some delta or any other criterion we would like. And with this encoding, we just feed that to a neural network verifier, and we can get a formal guarantee saying if the model and the circuit are the circuit is robust with respect to that input neighborhood, meaning its predictions are aligned with the full model around that perturbation domain. Okay, so that's just, this is a way we present how to certify if a circuit is input robust, how it if it implements our definition of input robustness. Okay, and the second notion we present here is the one of patching robustness. So as we said, a circuit is induced by patching the complementary of that circuit, all the components, all the neurons that are not in that circuit, but are in the full model to some value. And this choice is also somewhat ambiguous. I mean, existing patching choices can be zero patching or mean patching or other methods. But the value to put on the complementary is somewhat a choice that is a heuristic and not one backed by formal guarantees. And for instance, basically we have here, we should also remember that with these notions of patching, we basically evaluate on a finite set of activations like zero or mean, and that's maybe an example for that. That we can have this circuit that gets some value alpha on the complementary, and the circuit predicts correctly cat. But if we perturbate this and take some alpha plus some epsilon, we can have a false prediction, which means that this choice of patching values basically influence the circuit. So we basically want to give some more formal notion here of patching. And our definition is this: we basically want to have the circuit correctly predicting cat, which basically means that implementing what the full model does, not over some specific choice of activations, but rather on all feasible patching values that can be attained over a continuous input domain. So if we look at this continuous input domain, and we think if we take all the feasible activations that can be attained over this continuous input domain, we would demand that our circuit under all these feasible activations will be correctly predicting cat like the full model does. So that's our formal notion of patching robustness. Shahaf, would you like to add something?
Nope, sounds great.
Okay. So then we have this notion, and we also here ask ourselves, how can we certify patching robustness? So same thing, we designed this another encoding to achieve such patching robustness certification using neural network verification. So in here, we also duplicate the full model and the circuit. But to get this effect of considering all the feasible activations under some input domain, we basically do some neighborhood on the input. We specify some neighborhood on the input of this model of the upper network, which is only used to get the activations transplanted here in this lower circuit network. And then we, as you can, the lines here, the dashed lines here show that we take the patching, the activations from this upper network. And we have here the logics of the circuit, which we then define an output criterion that there will be aligned with the logics of the full model. So maybe I'll just repeat to be more clear. So we have this circuit network here that takes the complementary of this circuit takes its activations from the upper network, which is operating on a continuous input domain. And our output criterion is that this circuit with the transplanted activations is aligned with the full model. And this way, we show that we achieve the patching robustness notion of having the circuit correctly predicting or aligned with the full model under all feasible activations attained over this domain. And we feed that to a neural network verifier and get certified that the definition we showed. Okay, so another thing we show just briefly that one can also have this encoding, which we show that uses 3 networks to achieve simultaneous input and patching robustness, which means that this is a circuit where it's robust under input perturbations, while simultaneously and also robust under all the patching values that are attained over some patching neighborhood. That's also something that can be achieved, which with another encoding, maybe a bigger one with 3 networks that we show. Okay, and so far we introduced 2 robustness notions, input robustness and patching robustness, and we showed how we can certify this using neural network verification. And now we just show how our empirical results back this and how what is the experimental setup we used. So
by the way, there's a question in chat if you want to answer it before moving there.
Sorry, yeah.
Rembert is asking, could get, for example, be multiple continuous input domains?
One moment, I'll answer in chat. Sorry, I did not see the chat here.
Oh,
wait.
If you wanna open the chat, it's
yes.
The question was just like, right. It says like, is it like, could there be multiple continuous input domains for a specific that lead to the same output? Couldn't there? Isn't this making the assumption that one continuous, like all the space to like generate one output is all one continuous domain?
You ask sorry about the patching robustness or
like the input robustness? Like
yes.
Like how do you know for certain that for example cat I know for like the image models possibly like I buy that they're all like in that one continuous input domain, but like what about like for other types of models? Couldn't there be models that like don't have like one set of like maybe it's discontinuous, so like it has multiple set of input domains? How do you detect every single set of input domains? Because like I don't think they're all continuous.
Yes, so here we basically focus in this work on in this part of the robustness notions on the vision domain that has this kind of input continuous input. I hope I get your question right, but you ask like if you have set of inputs and how you can achieve continuity over them, or like in general,
or like
about
how do you verify that? Like I guess is it just a property of image models that like the set of the input domain is continuous for like outputting cat, for example? Is it like an assumption that's already like I just don't know if the concept of like the domain for like I guess like the image of like the bunch of cats like you showed on the slides, that one, like the BPE, like that's the notion in image models, I guess.
Yes, in image models, obviously it's not just about one sample. Like you can take a lot of samples and go and have some addition like of their surrounding neighborhoods. So that this is not we're not just talking about a single sample, but yes, it's maybe easier to think about on vision domain than other domains that continuous perturbations around the input are not very meaningful. Like for instance, language. You can look at the continuous perturbations around embeddings, but this is something a bit different than continuous perturbations around tokens.
Yeah, I just
Yes.
don't think this would apply to tokens. And I was like, probably,
Yes.
but that's like that was my gut instinct for tokens. So I wasn't sure. Like, I guess this is
Yes.
just proven for image models.
Yes, it's image, or if we look at, we also experiment here with some, also mainly for image or other types of data, but yeah, for language and tokens, it's a bit different setup than this
guess-
part of input.
I guess that the
Maybe-
classic
sorry, go ahead.
extension. I guess that the classic extension of this to a language would be to do some perturbation over a latent space, not necessarily around the tokens or something like that. 'cause
Okay, so yeah, latent space.
Yeah, there are some works that do generally verification in the latent space for language. I guess that would be like the most direct way to extend this. But this is something that, of course, needs to be done in a future work.
Okay,
How about for math, for example, changing names of variables, for example? That could be a perturbation, maybe.
Yeah, I guess that there are lots of different perturbation domains that one can think about. Each one will provide a different guarantee, of course. So I guess depending on the context, you could think of different potential perturbation domains.
Thanks.
For some reason, I don't see the chat here. Let's see.
If you go to the stream and click on top right, there's a bubble kind of button that opens chat.
Yeah. Great. Thank you. That was got it.
Okay.
Yes, thanks. So let's go back to, so we showed, as we said, two notions of input robustness and patching robustness, and we showed how we can certify this once we have some circuit to say if that's input robust or patching robust using some encodings we did that are fed into neural network verifier. And now we show some of our experimental setup and the results. So let's first talk about some general algorithm we use, which is building on the automated circuit discovery algorithm. We present this greedy iterative framework for circuit discovery. Well, this algorithm, as you can see here in this demonstration, it's basically traverses the network component by component, in this case neurons, tries to eliminate each one while preserving faithfulness. You see here it always checks the logits against another the full model, and it eliminates components if faithfulness is preserved. Otherwise, it keeps them until it reaches some discovered circuits. So this is basically a greedy algorithm that runs component, in this case, end to start, one by one, tries to eliminate them, checking faithfulness, and ends up with some discovered circuit. And we basically, our experiments focus on taking this, some of our experiments focus on taking this greedy algorithm and checking two variants, the baseline sampling-based variant, which basically its faithfulness is measured on some batch or like the set of inputs. And our provably robust variant of this algorithm, which certifies the input robustness or patching robustness on some continuous domain. So here we can see like the basic pseudocode where we have some iteration of all components, and we have the two methods. One is evaluating faithfulness directly on some set of inputs, and ours, which certifies that across some input or a patching domain, like we showed with the neural network verification. And so just one moment before we see the results and discuss them, we just say that we here focus on vision benchmarks. we use 3 classification tasks, MNIST, CFAR10, and GTSRB, which is a traffic sign recognition benchmark, and another regression task, which is called TaxiNest. And regarding we examine 100 batches of inputs, obtaining a circuit per batch. Well, I'll mention that the MNIST model is a fully connected neural network. The others are CNNs, and the granularity here is in the CNNs we look at circuits of filters, and in the fully connected one we look at circuits of neurons. And for the neural network verification, we mentioned this verifier that we use. So we use the alpha beta crown verifier, which is considered to be state of the art in that field. And let's maybe show our first results, which are the input robustness circuits results. So as said, we compare our sampling-based baseline and our provably robust method. For the input robustness experiment, we use 0 patching. We later have another experiment that we do on the patching robustness, but for this we use 0 patching, and we measure robustness over some input neighborhood, epsilon, around the pixels, and we report the average robustness as well as the average circuit size for the 2 methods and over the 4 benchmarks. So here what we can see is that we have this sampling-based circuit discovery, which is the baseline, and our provably robust variant. And we can see that our method, although slower in times because of the use of neural network verification queries that are sometimes computationally expensive, so it is somewhat more expensive in time comparing to the sampling-based the baseline times, but we show that we achieve comparable circuit sizes while maintaining 100% robustness, which is the result of us being certifying that, comparing to lower rates on the baseline method. So we see here some trade-off in time, but we see that we can achieve comparable circuit sizes with 100% robustness comparing to much lower rates on the baselines. So, and maybe some illustrative figure of that can be this, where we can see, in this case, that's a resonant circuit, which is part of the circuits we found on the CFAR10 benchmark, where we have here the baseline on the upper part. And this is the circuit discovered by the baseline method of filters. You see them here in blue. And when this circuit gets some noised image of a bird, although the noise here is barely seen, but there is some noise here apparently. And when it gets this noised input of bird, it falsely classifies it as deer. Whereas our provably robust method discovered circuits, while it retains some more filters, you can see them here in green, it correctly predicts it as bird. So that's basically maybe an illustration of the input robustness notion that we certify and can achieve in our framework. Okay, and the second result we would like to show here is that of the patching robustness. And so we also here examine patching robustness over some patching domain, which is the feasible activations attained under some continuous input neighborhood. And we compare our method, which certifies that, against some baselines, which are 0 patching and mean patching, which is fixing activations to some mean over selected sample set. And here we have the two baselines in our method, and we can see that again we have some trade-off in times, but we see here that again we can achieve comparable circuit sizes to the baselines while maintaining higher rates of robustness. And yes, I see here some question in chat. Looking at the results. Yes, so that's a great question. Mostly, if I was asked here if robust circuits mostly contain the same components as the unrobust plus a few nodes. So that is something that we've encountered and also a few times. It's not always the case, but usually, I mean, you can think of it as that sometimes, I mean, it's not. This is not the case that it includes just additional filters, but it often intersects with the ones discovered by the sampling variant. And here, yes, it is the case that some filters are added, but that's not always the case. So maybe I answered that. My explanation was a bit unclear, but we sometimes see that, yeah, this is just some added filters, but sometimes not. It's not always the case that sometimes the computation is done through other routes and is not only adding some more filters to the baseline one.
We also have in the appendix an analysis of the IOU intersection over union and measures like that show relations between
these
different circuits that were found in the experiments. So this analyzes this.
Yes. Okay. Sorry. Yeah. Okay, I see someone is typing, so I'm gonna wait for another question. How do we know when to stop adding more noise? There seems to be travel between volatility and too much noise. In some context, okay, so regarding the noise, so yeah, that's a great question. How do we choose what neighborhood to look on to examine? And we do some variations of this in the appendix 2. We observe several different values for this epsilon, which means several different sized neighborhoods. And we show there too that this distinction between the baseline and the robustness of our probably robust method and the baseline also is preserved, the difference between these two. But yeah, that's a good question. Like, what epsilon should we pick? I guess it depends on the level of the specific type of inputs and what the circuit we want to have eventually. And I see also in some contexts we probably can't try all possible perturbations to be one pursue that the second one we can't get more. So here that's maybe the thing we show here, that using formal neural network verification we can check all the perturbations. I mean, it's not just we examine some set of perturbations, and neural network verifications allows us to achieve certification across all feasible perturbations in that epsilon neighborhood. So
okay, I see. Yeah, my thought
so-
was also that for some tasks, like you could design a lot of different perturbations that you just don't capture with the, like when you are defining the neighborhood.
Yeah.
So
Mhm. Yes, here we
like
can.
some attacks that are not just adding noise, for example.
Yes. So that's but that's a good also thing that I also come to think about. And could you find multiple circuits? I mean, so here we look at this greedy traversal, and in that case, we go one by one, and we end up with some certain circuit. But obviously, if we decide to go from start to end, then we can achieve a different circuit. And also the choice of epsilon here changes the circuit. So we have some, let's say, design choices in this routine of circuit discovery that can yield different circuits. But once we look at this end to start ordering, and once we set this epsilon, we achieve the, I mean, because this is a greedy operation here, we achieve the grid deterministic operation here, we achieve the same circuit. So is that answering? Is that okay?
Yeah, that's good. Thanks.
Thank you. Okay. So yeah, now so we showed some two notions of input robustness, patching robustness. We show how can we achieve them and show our empirical results concerning them. And now we discuss circuit minimality, which is another formal guarantee we present here. And maybe this is this is the part where we show some more theoretical results. And so intuitively, smaller circuits in size are considered more interpretable. I mean, a full network is always a circuit. It's faithful to itself, but that's pretty trivial, and we want to have smaller circuits as possible, maybe. But what can be stated formally about the size of circuits? And so we first start by defining 4 definitions of circuit minimality. And from weakest to strongest, have quasi-locally subset cardinally minimal. We will be showing them briefly. And then we can prove a connection between these notions and circuit discovery algorithms. So let's have this running example of a network, of a Boolean network, and that takes inputs x1 and x2 that are either 0 or 1. And it has some multiple nodes, which you can see here, v1, v2, v3, v4, v5, v6. And these are aggregated by XOR to output some y. And this is a running example which we will show our robust minimality notions on. And so if this big network actually simplifies to just computing return, like outputting x2, if you can see the math here, just remember that XOR of something with itself is 0, and XOR with 0 is XOR of something with 0 is that something. And basically we will be looking in this running example on a case where we demand our faithfulness predicate to be actual exact equality. So basically, we want to find a circuit that is exactly outputting the same results for all inputs like the full network, which basically means that we will look for a circuit that always for every input outputs x2. And maybe I'll just show some the notions themselves, and it will be more clear. So our first weakest notion is quasi-minimal, which is given some network G like this and some faithfulness predicate, a circuit is quasi-minimal if it has some element that removing it will break the faithfulness of the circuit. So we have some quasi-minimal circuit is a circuit of this full model that contains one element that if you take it out, then that circuit is no longer faithful. So in this case, remember the full network is computing just X2, and we want to be having a circuit that is exactly like the full network, also predicting X2. So in that case, if we look at this set of components, V1, V2, V3, 4, and 5, we have here some element that if we take that out, and this group will, this set will no longer be a valid circuit, which is the V1. If you take that out, the XOR of X1, of V2, V3, V4, and V5 will not be resulting in X2. So that's an example of a quasi-minimal circuit. And a stronger notion, stronger definition is the one of locally minimal circuit, which is a circuit that does not only contain one such element that taking it out will be breaking faithfulness, but all for any of its element, if every element is a breaking point. I mean, if we take every element and outside of the circuit, we'll be breaking the circuit's faithfulness. So in this case, we can see that V1, V2, and V3 is a locally minimal circuit, because taking V1 obviously results in X1 XOR X1, which is not X2, and taking V2 or V3 will be resulting with a different computation of X1 XOR X2, and this is not a. So yeah, this is an example of a locally minimal circuit, and we prove that if we take some greedy iteration algorithm, an exhaustive greedy iteration algorithm that always tries to eliminate in a greedy way the components while preserving faithfulness, this one converges to a local minimal circuit. So that's some connection we prove between the definition and discovery algorithms. And we will now show some stronger notions of minimality of circuits. So we showed quasi and local. The next one is subset minimal, which is a circuit that's not in locally minimal. We said that every element is a breaking point. Here we say that a stronger notion of that's not just any element is a breaking point, but even taking a few elements at once will be a breaking point. So maybe to make that more clear, here in locally minimal, we said that taking each element breaks faithfulness, but here we could have taken, for instance, V2 and V3 both, and we will be resulting with a valid circuit. So locally minimal means that you cannot take each one, but if you can take a subset out and still be obtaining a valid circuit. So subset minimal is, as we said, the stronger notion that not only that we have this circuit that taking any of its subsets outside of the circuit will be breaking faithfulness. So in this case, V2 and V4, we cannot V2 and V4. If we take the XOR, that's X2, but eliminating V2 or eliminating V4 breaks faithfulness. So yeah, all the subsets of this group of this set is required. And we proved that the greedy iterative algorithm is not guaranteed to reach a subset minimal circuit. And we show some examples of such circuits. So such configurations that do not reach subset minimal circuits. And the question is, can we reach subset minimality, which is a stronger notion of minimality? How can we achieve such strong minimality guarantee? And for that, we introduced the notion of monotonicity, which is, we use this notion of monotonicity to later prove that we can achieve subset minimality. And monotonicity is basically the notion of adding some a neuron to existing circuit does not break its faithfulness. So basically, if we have some circuit, which is a subgraph of the neural network, and we add some component to it, in this case, this blue marked neuron, then that will be a faithful circuit too. So monotonicity says basically that if we have a faithful circuit, like this one here on the left, adding some component, in this case, the blue marked neuron, will be resulting in also a faithful circuit. And so that's a property that we define. And interestingly, we show that some connection between input and patching robustness and this property. We proved that a certain simultaneous and input and patching robustness setting, like we showed before, is actually a monotonic predicate. So we show that interestingly. And what we prove is that under monotonicity, under this property we defined, the iterative greedy algorithm converges to a subset minimal circuit. Okay, so here we show theoretically that you can achieve these strong notions of minimality through the notion of monotonicity. Yeah, and so for this faithfulness predicate that is robustness based that we showed, then yeah, we can obtain subset minimal circuits. Okay, and just the last notion of minimality we have is cardinally minimal, which is a circuit. This is the strongest notion of minimality, which basically means that this is the circuit that there exists no circuit with smaller cardinality that is a faithful circuit. So a cardinal minimal circuit basically means a circuit that there exists no smaller circuit in size that is faithful. In this case, obviously here, this is a cardinal minimal circuit because there is no smaller set than in cardinality than that can implement the full network computation, which is X2. Okay, and can we say something about this strongest minimality? And so for that, we approach the problem from the opposite direction, and we present this duality, but first we just say what this duality is about. So we introduce the notion of circuit blocking sets, which are sets of subgraphs that's excluding them from any circuits break faithfulness. So basically, this can be seen as a neuron that excluding that from any circuits breaks the circuit's faithfulness. So any faithful circuits should include them. And in that case, we mark this in blue, and you can see that any circuit that puts this in the complementary is resulting in an unfaithful circuit, unfaithful predicate. And we establish a duality that uses this notion of circuit blocking sets to achieve cardinally minimal circuits through something called minimum heating set. So I will be going very briefly on that, but just a minimum heating set, a reminder is if we have a few sets, then a minimum heating set is the smallest cardinality of a set that intersects with each of these with all of these sets. So in this case, we have a few sets in different colors, green, orange, red, and the smallest set that intersects with all of these is 2 and 6. You can see that. So that's a minimum heating set. And now we just, let's talk about this duality. So we show that under monotonicity, the minimum heating sets of all circuit blocking sets, all the components whose exclusion from circuits breaks faithfulness. So the minimum heating sets of all these circuit blocking sets is actually a cardinally minimal circuit. So here we can, this way we are able to talk about the strongest cardinality one can obtain. And this leads us to this following algorithm of just searching blocking sets by increasing size. First, let's look for one neuron, contrastive neuron, and then take pairs of elements that back faithfulness, and then triplets, and computing their minimum heating sets. And we proved that we can stop. We can look at all the enumerate all the different sizes. I mean, we go from singletons to pairs to triplets and so on. But for any size we stop in, we prove that this algorithm returns a circuit whose size is actually a lower bound on the cardinally minimal circuit. And if we go all the way with and enumerate all the possible sizes, then yeah, this algorithm converges exactly to the cardinally minimal circuit. And we show that also empirically. And here we experiment with that, and we show that we have here some a quasi minimal circuit, which is something we did not discuss here, and we also have the iterative algorithm circuits. We have here the circuit size and the MHS size, the MHS algorithm size, the duality algorithm size. And we show that first, this MHS size always lower bounds other methods. I mean, you could, as we said, this is the you cannot achieve a smaller size than that. Although the iterative stage sometimes approaches near it, and we can see that some of the MHS sizes which were found to be faithful are also on this line. I mean the MHS circuits, yeah. And here we can also see the trade-off in time, where the iterative search is actually gives smaller circuits at the lower runtime, and MHS is slower, but it, as we said, approaches the cardinally minimal size. And for these experiments, just to say some note that was written here, and I forgot to say that we experiment over MNIST, and this blocking sets that we check in each stage, this can be done in parallel, as this is not an iterative circuit discovery where we have to eliminate Y component and then go for another one. Here we can look for blocking sets in parallel, and we did parallelize that over 14 workers. That's a technical note. And yes, we can see here how this MHS algorithm lower bounds the sizes of faithful circuits, as we showed, with some trade-off in time. And so just a conclusion of what we showed here. So we introduced this framework for circuit discovery, where we presented two notions of robustness, input robustness and patching robustness, and some notions of formal guarantees concerning minimality of circuits. And we used neuronal verification to obtain this certification of input and patching robustness, and experimented with that against existing sampling-based baseline methods. And we showed also, on our way to achieve stronger minimality, the notion of circuit monotonicity and the principal connections. We also show between robustness and monotonicity, and with that we even show that one can achieve the strongest minimality of circuit, which is the cardinally minimal circuits, using some duality we formed. And so that's about it. We'll be happy to take question if there are.
Just a comment. I thank you for explaining this. I don't think I looked too much into like formal verification before, so this is pretty cool.
No, thank you. Thank you. Thank you very much.
Maybe a question.
Yes.
Have you thought about this in the context of alignment, essentially, or not much in this direction?
In the context of alignment?
Yes. So, like,
Mhm.
I don't know, maybe like how to make provably guaranteed, like, internal circuits that don't include deception or something like that, for example.
Yeah, well, that's a very interesting and important point. And so here, because we focused on the vision, we can think about faithfulness of, for instance, in the benchmarks we presented, we can have, let's go back to that, sorry. Here we would like to, in this kind of benchmarks or we can be talking about this safety of the circuits. I mean, if we have a circuit using our framework here, we can achieve a circuit that is robust with respect to perturbations on the inputs here that are sometimes related to safety. But yeah, I guess your question mainly concerns language models that have some more sophisticated notions of alignment. And we did not experiment with that, but yeah, that's a very important and interesting direction for sure.
Okay, thanks.
I guess that extending like that we're looking already for this for future work, but extending this to other perturbation domains, statistical variants, and yeah, it's a question of how to extend this to maybe to like we spoke before about looking maybe at the latent space domain. How can we certify a domain that has some, I guess, meaningful semantic meaning in the context of language models? I think this is like an important question here.
Yeah.
So you can think maybe of this as like, I guess, a first step, and then using maybe a similar idea to extend this further.
Or maybe every time there is some verifiable output, you could generate synthetic data which should equal the same verifiable output in math, for example. So some of the math, not all of it. That could be one way to specify the neighborhood, maybe.
Yeah, to talk about verification in this setup, yeah.
Yeah.
Mm-hmm.
So like
also, go ahead.
Yeah, so in your definition for robustness, like these epsilons and deltas are like independent, right? Like epsilon does not have to depend on delta.
You mean the ones here, the epsilon and deltas. Sorry for being so slow and scrolling. Let's see. Yeah, you mean these ones.
Yeah. So like saying that epsilon depends on delta, would that be like a strong condition? Like for every delta, you can find an epsilon.
And so I don't think they are dependent in that way. I mean, epsilon is obviously the neighborhood size, and delta is the alignment, let's say, in logits. If you take a smaller delta, then you force the full model and the circuit logits to be, let's say, closer. And it also depends on the faithfulness metric and things like that. But so I guess they are not directly dependent. You can have, we actually included the variations in the appendix of both delta and epsilon. But I guess if we take a bigger epsilon and we take small delta, then it will be harder to, I mean, the circuit will have to maybe intuitively include more components to be aligned. I mean, smaller delta maybe requires bigger alignment with the model, and bigger epsilon is over a bigger neighborhood. So maybe that will require our circuits to be bigger and more like the full model. And I don't know if that answers, but yeah, these are separate. I mean, you can vary the epsilon and delta, and they are not correlated or something.
And also, like,
Yes,
your definition, like, it doesn't have to be true for all inputs, right? Like, just you choose some batch of inputs.
You mean in our experiments, the input robustness notion, or
The definition, yeah, because you're not saying for all input X. You're just saying like for some batch of inputs X, right?
so we do talk about all inputs X, like if like the main methodology is taking some batch of inputs, let's say a batch of images of cars. So we consider continuous domains around each sample. For instance, that and that's how we talk about it. So yeah, we consider I mean, if the general methodology is taking some batch of inputs and finding a sample set and finding a circuit. So we look at all the continuous input perturbations around all the samples.
Right.
Like you could theoretically look at the entire perturbation domain, right? So you could theoretically say, okay, if it's like an image and let's say it's normalized, so it's between 0 and 1, so we're actually verifying that for the entire possible domain, the circuit behaves like the original model. But this would probably be too strong of a notion. So for this reason, we are limiting the perturbation domain to be epsilon balls around a bunch of images that we know of. And of course, as I said before, like this, looking at other different perturbation domains could be also interesting for future work, like looking at the latent space or looking for maybe perturbation domains that have some semantic meaning or other ideas could be interesting. And regarding the comment on the delta, I think this is like really similar to in the classic ACDC paper, what they call tau. So they have this tau parameter that you're looking at the KL divergence metric will always be above some tau, and then you can play around with this tau. So if it's large, right, or small, there is some trade-off. So it's either that you'll have that the circuit is, I guess, more faithful, or that you'll have that the circuit is. So if it's more faithful, it will be larger, and if it's less faithful, it will be smaller. So it's, I guess, some granularity level that you need to play with.
For the perturbations on latent space, something that seems relevant is the recent Goodfire papers about finding manifolds on the on activation space, where they claim some features are represented on some continuous manifold, where as you can move on it and have some part of the output or something about some circuit change in a smooth way, it seems like there could be something there where you could do something like this to check that or something.
Yeah, I think it's an interesting direction. Generally, need to think about it a bit more. But yeah, I think any extension to other meaningful perturbation domains could be really interesting direction.
Yeah, perturbations around steering vectors that are linear directions, perturbations around SA features that are also technical linear dimensions, directions, but disentangled more, and perturbations around the manifolds, as Victor said, or maybe also around circuits in the cross-layer transcoders from the biology of L paper from Anthropic, for instance. That might work, maybe. Somehow in latent space.
Yes, totally agree. I think I see this like as a first step, like in formalizing some of the stuff in general, and totally agree that there are lots of potential ways to define this.
I guess, like,
Oh, go ahead.
I guess, like, I was thinking that it seems like you could, like, the good fire people are, were claiming things about, how steering with the manifolds was better than steering with the linear probes, for example.
Yes.
That seems like they should be, you should be formalized as some kind of something like this, where you say something about like you can more easily find circuits that, or you're trying to find circuits, you'll find that they are robust to perturbations through along the manifold, but not on the linear direction, because that breaks how the model represents. Because like that's in some sense moving from a part, not moving smoothly through the part where the circuit works.
I need to think about it a bit more.
Yeah.
But yeah, I guess in any place where you can have perturbations and you can use neural net verifications to certify that, and yeah, that's also applies to manifolds and other types of setup sig. But yeah, I that's a very cool thing to think about. Yeah.
I still have this feeling, at least with these neural models, where the various things are very fuzzy often, that for sufficiently complex behaviors, that like there's, at least with everything I know so far, there's not 100% guarantee that the model will not do something that you don't want, for instance. Since, I don't know, even if you have some circuit and some perturbations around it and so on, there might be some other equivalent circuit which you just didn't identify, for instance.
So there are extensions of neural network verification to there are lots of works on statistical verification as well, which is also like a classic, I guess, extension of what we did. So there you could, for example, look at some, I guess, statistical guarantee. It's not necessarily 100% of the time, but for some, I guess, probability statistic, you want it to hold. So I guess I don't know if that answers your question. So the guarantee would be like less strong, more scalable, and you have this flexibility of it doesn't need to hold 100%, but let's say for probability above some threshold, let's say something like that.
Yeah, that's also good. Also, maybe another question is: are you familiar with what Mechanistic and some others are doing in us trying to automatically verify or provably verify safeness of models, basically?
Which group are you talking about?
In chat, I say you sent that in chat. Yeah, I'm not familiar.
From Mechanistic, Steve Obubububo also did that, and a bunch of other people. Yeah, these papers at the beginning. I haven't read those papers, so I'm just if you're aware, I don't know.
Yes, we look at them. There's actually one paper that followed ours, which is one extension that what I said for statistical guarantees. That's called certified circuits. You can also look at that one. But I don't know the specific paper you're referring to. So definitely look it up as well.
Yeah, thanks for the video. Looks cool.
Okay, thanks. Yeah. I think those are also into like neurosymbolic systems where you have some more, where you can do some formal stuff more.
Yeah, maybe that's awesome.
If you're generating only Lean then or only Rust, then yeah. There you can have certain guarantees for every single output.
Oh.
I'm not sure exactly what Mechanistic is doing though. Yeah.
Yes, there is also the paper for decompiling transformers to Rasp. I don't know if.
Yeah, we read it on this reading group.
Yes, I saw it as well that you went over it. So in Rasp you can also like verify certain properties. I guess yeah.
True.
The problem is like if you lose some of the faithfulness in the decompiling process, I guess.
Yeah, I don't think that there is like a great way of decompiling yet. Like I don't remember that much of the paper. I will have to go look at it, but my vague memory of it was not that great of a way of in practice for real models to decompile it, actually decompiling the model.
Yeah, it was mostly. Yeah.
Oh, sorry,
it was mostly very simple circuits.
Yeah. And even then, it seems like it had like some parts that were kind of not that automated. Like they work because they kind of did a lot of manual work of identifying some kinds of patterns in models and make it so when they were detected when those happens, but it will be hard to do the same kind of thing we're doing for everything. But yeah, maybe there is some nicer way of decompiling things in Rasp. And that doesn't just give you like the model, but writing as a giant Rasp program that nobody understands. I guess maybe if nobody understands, you will still do formal verification on it, but I'm not sure that's better than just doing it like you are doing here on the network directly.
Yes, I guess like the main thing is like if you decompile to like a smaller model or to a smaller representation, it would be like scalability wise easier to deal with it. But the problem is that you lose like probably a lot of like what the model represents this decompiling process. But maybe there's some trade-off here, right, that can be explored, I guess.
Yeah.
So like I don't know much about this formal verification, but like is it the case that with any MLP like you can verify if like a epsilon ball lands in a delta ball? Like is that possible for any neural network?
Yes, but under piecewise linear activations, you can also have some approximations on non-piecewise linear. But let's say if your MLP uses piecewise activations like ReLU, then yes.
There's also extensions for like other activation functions. It is true that it's like it's not complete, meaning that it doesn't have to converge to a final solution. It can also say like, I don't know, if it's not a piecewise linear, but in practice, there's also like a alpha beta ground that is implemented on like vision transformers and stuff like that. But it works, I think, the best on CNNs, ResNets, MLPs, stuff like that. This is like the scalability wise, I guess the best. It's the best on those. Any other questions?
Thanks.
Okay. Well, thank you very much again for having us. And
Thanks for coming. Yeah, I guess I'll stop the recording.
cool.